Hello everyone. Today we are going to talk about QuickSort. QuickSort, like MergeSort, is also one of the most efficient sorting algorithm, and we're going to see that how it works. Similar to MergeSort is also a divide and conquer approach. So here on the right side of the board, you see the pseudocode of the QuickSort. So given an array and the lower index and the highest index you have, we are checking if the low is less than high. And if this is the case, then you are calling another function called partitioning. So you call the partitioning that returns an index. We call it the pivot number or the pivot index. Then you are calling the quicksort for the lower index up to the pivot -1, and then you're calling the quicksort again for the p+1 and to the higher number. So what happens is that p, or the pivot number that you're looking for, divides the array into two sub-arrays, and then you are calling the quicksort again on those two sub-arrays. So what's the use of this pivot number? Okay, so the pivot number is a number that after you are finding that, you are putting it at its place. So every number before that pivot number will be less than the pivot number, and every number or every item at the right of the pivot number will be greater than the pivot number. So like one by one we are solving like sorting the array, okay, using this pivot number. So you may choose the pivot number, let's say like the first item, you can put it as the first number, or you can put it as the last number. So it's up to you that which like pivot number you want to choose, what's going to be your pivot index. So here let's do our example on this array A with 6 numbers, and let's see what we have. So we have n equal to 6, we have L is equal to 0, and high is the n-1 that is equal to 5. And now the question is that what's going to be this pivot index. So first of all, what we are going to do is we are going to go to the details of the partition function and see how the partition function works. Then we'll go back and solve this sorting problem using the quicksort. This is the partition function that we're talking about. So we have the array A with the lower and the high index, that in this case lower index is equal to 0 and the high index is equal to 5. So we have the pivot index equal to the lower index in this case, so we chose 7 to be our pivot index. So the 7 is going to be the pivot value, and like the pivot index is going to be the low index that is equal to 0. Now what we're going to do is put 7 at its location and put every other number that is before like is less than 7 to the left side of 7, and any number that is greater than 7 to the right side of 7. So at first j is equal to 0, also I is equal to L, that is also equal to 0. Now we are comparing A at location I, okay, with the value of the pivot that is equal to 7. Okay, so here we are just ignoring this because I and L so far are same, so we are going and we are here we are increasing j, although I mean there are A of I is less than equal to p value, so we're increasing j, so now j becomes 1. Okay, we did the comparison of like the pivot value with itself, so j becomes now 1. Now we are going back, so we're increasing I, so I also becomes 1. And now what we're doing is we are comparing the value of A at location I, that is number 3, okay, with the pivot value that is equal to 7. And because 3 is less than 7, less than equal to 7, okay, we are swapping the value at location I with the location j, and because both I and j are equal to each other, so there's no changes, but we are increasing j, so j becomes now 2, and also we are increasing I, so I also becomes 2. Then we are comparing the A allocation I, okay, and also the pivot value that is equal to 7. So 2 is also less than 7, so we are like swapping the value of A of I and J, both are same. Okay, so there's no actual swapping. So J becomes now 3, and also I becomes 3. The next value that we're going to compare is A allocation 3 with the pivot value that is 4. And because 9 is not less than 7, okay, so we are not increasing J, so J still is 3, but I now, after leaving I, gonna be number 4. Okay, now I is 4, okay, and so the next value that we're going to compare is A allocation 4, that is number 4, and because it's less than 7, so we are swapping A allocation I with A allocation J, and J is location 3, and I is equal to 4. So it means that we are swapping the value of 4 and 9. So here, this will be 4, and this will be 9. Okay, so that's gonna be happening. And we're increasing now J, so we're increasing J. J also becomes 4, and now I becomes 5. So after we are going back to the for loop, so I becomes 5. Now we have number 8. That number 8 is not less than the pivot value, so there is no like the swapping. And now we have number 7, 2, and 4 that are less than 7, and we have number 9 and 8 that are greater than 7. So at the end here we have the swap operation that we are saying that swap the value at the array at location j-1 with the array at location the pivot index. So here number 7 will be swapped the value at location 3, that is going to be number 4. So if we have the number 4, so it's going to be 4 here, and number 7 will go here. Now if you look at the array, as you see that 4, 3, and 2 are less than number 7, and 9 and 8 are greater than 7. So that's that's the location of 7, and 7 now it's at its location. So the rest of this, the QuickSort is after we got this the new pivot value, the pivot value that is j-1, that here in this case, in this example, is equal to 3. Now we're gonna call the QuickSort, okay, calling the QuickSort for A 0 and p-1 that is equal to 3 minus 2 is going to be 2, and also we are going to call the QuickSort with array, and the p+1 that is going to be 4, and here also 5. That means that we are going to call the QuickSort for this sub-array that contains number 4, 3, and 2, so these 3 numbers. And also we are going to call the QuickSort, okay, for the number that starts from the index 4 up to index 5 that contains number 9 and 8. Okay, so similar to what we did for like this part, okay, for like putting a 7 at its location, we can do the same thing. So like we are going to continue our example, okay, to finally sort this array together. Okay, let's continue our example. And now we have the first subpart of the array, that is the QuickSort of array A, and from index 0 to 2. Again, we are assuming that the pivot index is equal to 0, so the pivot value is going to be 4, and I and j both are equal to 0 now. But this time, h, that high index is going to be 2, and still the low index is going to be 0. Now again, we are going from I equal to low to high. So at first I is equal to 0, and now we are comparing A allocation I, that is number 4. We're comparing with number 4, and because it's less than equal to number 4, then we are swapping the numbers. That doesn't do anything, but it increases J. So now J becomes 1, and when you're going back to the for loop, also like I will become 1. Now we are comparing number 3 with number with number 4, and because 3 is less than 4, so we are swapping array at location 1 with location 1, that is 3 with itself, no changes, but we are increasing j, so j will become 2, and also next also j will becomes I will also will become 2. Now we are comparing 2 with 4, and because 2 is less than 4, so we are swapping the values of 2 at location, like array location 2 with also array location like the j, that both are the same, so there's no changes, but we're increasing j, so j becomes 3. And now because we are at the end of the sub array, okay, we are not doing any more for loop, so we are going out of the for loop, and we are swapping the array at location j minus 1, that is going to be a location 2 here, okay, with array at location the pivot index that's going to be 0. So we are swapping the number 4 with number 2 here. So let's here, so here it's going to be 2, and here this is going to be number 4. And as you see, number 4 now it's at its location. So in this sub array, number 2 and number 3 are both are less than 4. So, and also we don't have any other thing on the right side. So number 4 is its location. Now we are going to call the QuickSort also for this sub array. So first of all, what we are returning is j minus 1. So we are returning that's going to be p. So p is going to be j minus 1, that is going to be 2. Now for this sub array, okay, we are going to call the QuickSort of a and low and p minus 1, that is going to be 1. And also we are going to call the QuickSort a and p plus 1, that is going to be 3 and 2. Okay, but here, because we don't have like the low is not less than high, okay, if you go back to the definition of the QuickSort, you see that because we said that low should be less than high to go inside the functions, because low is not less than high, so we are not continuing this part. Okay, now we only have this part, the QuickSort of a at location 0 up to 1. So that's gonna like have just put the 2 as its location. And because 2 and 3 are both sorted, and also we have the 4 is at location, so this part of the problem is solved. Now on the other side, we had the QuickSort of a and at location 4 up to location 5. So that is this part. Okay, so if you we want to like write the values here. So here in this case, L is equal to 4, I is equal to 5, I is equal to 4, and J also is equal to 4, and the pivot index is equal to 4, and pivot value is equal to number 9. Okay, now we are checking the number 9, okay, with number 9 itself. Okay, there's it's less than equal to the pivot value, so we are swapping and we're increasing j, so j becomes 5, and also I, for the next round, also I will be 5. Now we are comparing the value location 5 with our pivot value that is 9. So because 8 is less than 9, so we are increasing j, so j becomes 6. And we are swapping the value at location I, that is 5 with itself, so there's no changes because 8 was going to be swapped with itself. So now what we're going to have is that we are swapping the now at the end we are going to swap the values at location j minus 1, that is going to be 5, with the A at location low, that is, or the pivot index is going to be 4. So now we are swapping these values, 8 and 9. So 8 goes here, and also 9 goes here. So we had put 8 at its location in the array. And then we have number 9 that is here. So we are returning j minus 1, that is, so p will be equal to 5 here. And so it means that we need to call the quicksort array low is equal to 4, and p minus 1 is going to be 4. And the quicksort of a and p plus 1, that is 6 and 5. Here, in both cases, because low is not less than high, okay, so we are not going to call these two functions here. And as you see, the array is sorted. We have number 2 here, number 3 here, 7, 8, and 9 that are sorted. So that's how the quicksort works. Now let's talk about time complexity of quicksort. Quicksort, as you found out, so it uses a pivot index, okay, to divide the array into two sub-arrays. So in the best case, or if we can, the pivot number, the pivot index can divide the original array into two almost equally sized subarrays, then we will get like our best result. The worst case scenario happens is when the pivot value that we just randomly chosen, is either the largest number or the smallest number. So if it's the smallest number or the largest number, okay, all other numbers will go to the right side. If it's the smallest number, all the values should go to the right side of that. And if it's the largest number, all values go to the left side of the array. So let's write some example here. Let's say we have an array B here, and we have 1, 2, 3, 7, 4, 9. Here, let's say that we are choosing this one, number 1, as the pivot value. As you see, all other numbers are at are greater than 1, so we are going to call the quicksort for array. Let's say here's array B. Okay, so I'm gonna put array B, and the pivoting is gonna be from low, that is here in this case gonna be for example 1 to the number that we have here, that's gonna be we have 5, so it goes from 1 to 5. And the other quicksort cannot be called, okay, because there is no other values on the left side of the array, so all we have on the right side. Okay, but let's write it what we had here. So it was the quicksort, and low, that was 0, and p minus 1, that is here 0, is going to be minus 1. So there's no way to call this one. So as you see, this subarray, okay, this subarray is from almost like the size of n, always n minus 1. Okay, so what happened is that actually we haven't reduced the size of the subarray significantly. We just reduced it by 1, so that's not going to be good. If we have a tree, for example, okay, so at first we have size of n, then we have a size of n minus 1 and n minus 2 and until we reach the size of array size of 1. So together, if we sum these numbers together, it will be number 1 plus 2 plus n, then together we're going to be n, that is let's write it this way, so it's going to be from big O notation of n squared. So the worst case of the quicksort will be n squared. But in the average case, let's create another one here. And what's going to happen in the average case is we can almost like what we had here, the example that we had, array A, okay, that we were able like to put the 3 numbers on the left side, so we had number 7 here, and then we had number 4, 3, and 2 this side, and number 9 and 8 on the other side. So almost 2 subarrays of equally like with this equal size, almost, okay. So we have here n, then we have n divided by 2. Here we have n divided by 2, n divided by 4, n divided by 4, and at the end we have the leaves that are all 1. So these are almost we have n leaf here, and also the height of the tree will be log n. So together we'll have the average, like the best case of the like the quicksort gonna be n log n. Also the average case of complexity of the quicksort is also n log n.